All right. So for this video, we're going to cover topic number 46 in lecture 15. All right, which this goes over equilibrium in 3 dimensions. So just as in 2 dimensions, we have to, our first step when we're trying to evaluate equilibrium problems in 3 dimensions is we're going to need to draw our free body diagram, right? So to draw our free body diagram for a rigid body, we have to know a list of some common support reactions, or common supports that are used in structures. So typically different supports will provide either a reaction force or they will create a reaction moment. So a reaction force prevents translation of a rigid body, while a reaction moment prevents rotation of a rigid body. All right. So there are some special cases that I want to highlight. In the next page, there's going to be a table that will go through the different types of common support reactions in 3-dimensional rigid bodies. So there's some cases that will have a varying number of support reactions. All right, the first case is in the case of single journal bearings, which are numbers 5, 6, and 7 on the table on the next page. And then for the next one is the pin and hinge support. So that's number 8 and number 9 on the following page. All right. So for these types of supports, we have so if there is greater than one of these supports attached to the rigid body, the reaction moment will be treated as redundant. And may be left off the free body diagram. All right, so this assumes the bearings are properly aligned and installed. Right. So if we go to the next page, you'll see that there's a list or a table of the different types of support reactions that are available. So there's some of them are common to what we talked about in 2 dimensions, such as these 3 types of connections. These all have one reaction force. All right, and then we have the ball and socket joint, which prevents translation. So it has 3 forces, so 3 unknowns, and then the rest of so for example, the single journal bearing has up to 4 unknowns. So it has two forces, Fx and Fz. All right, and then it has two moments, Mz and Mx. However, if you have multiple journal bearings that or if the shaft or whatever the journal bearing is supporting is supported elsewhere, you should not include the couple moments. All right, so these are sometimes not included. All right, and this is true if we go to the next page. The other journal bearings, if you look at them, so for the other journal bearings and for the pin and hinges as well, is that they also include this condition where if the rigid body is supported at some other place, you would not include the couple moments. All right, so please be aware of that. All right, of this condition. All right, and then the ultimate support would be a fixed support, which would be able to apply 6 knowns, six reactions, 3 forces, and 3 moments. All right. So here's some examples of the different types of supports. So we have an example of a ball and socket joint. We have an example of a journal bearing. And then we have examples of a thrust bearing and a pin support. Right? So just like we had in 2 dimensions, it's going to follow the same procedure to analyze the rigid bodies. So we're going to do an example problem that will go through that procedure. So you first draw your outline shape, you'll define your coordinate system, you'll draw all the forces, and then you will add all the reaction forces due to this body support. Right. So if you go to the next page, we'll do an example. All right. So the first step is that you should outline the shape of the rigid body. All right. So 1 will outline the shape. All right. So if we outline the shape, what we'll end up getting for this rigid body here is we'll have, and you don't have to make these too complicated, just draw the general shape of the body. So here I'll include the points A, B, and C here. All right. Then the second part of the problem asks you to define the XYZ coordinate system. So all right. So that's for us. Then the third part of the problem asks you to define to apply the external reaction forces. External forces. All right. So in this case, we have a couple moment that goes about the 45 newton meters. It goes about around the shaft at point A, and then we have another force that's applied at 500 newtons down. All right, and then the last part is to apply our reactions. So if we look at the problem statement, it says we have 3 journal bearings at A, B, and C. So since we have multiple bearings, we'll have no couple moments. due to those bearings. So for at point A, the shaft goes along the x-axis. So we would say that it would resist motion in the y direction and along the z-axis. So there'll be two forces there. All right, and then if we do the same thing for B, the journal bearing goes along the y-axis, so it would have supporting reactions in the x direction and the z direction. Right, and then if we look at C, C's axis goes along the z-axis, so it would have supports along the y direction and along the x direction. All right, so that is your free body diagram. All right, you may stop the video at this point and try to do the other two free body diagrams before continuing in the video, and you can see how well you did after I try. All right, so you want to stop the video now. If not, keep going. I'm going to keep going here as well. So we had for this free body diagram here, we have a so we're going to first draw the shape of this. So we have a rod. All right, that's at a 90-degree angle. All right, our x, y, z coordinate system will define just like we had before. So I'll have it as, all right. And then we have, in addition to this, we would have a, so then we have to apply our external loads. So we have a 300-pound load going along the z-axis, and then we have a 200 Newton meter couple moment that's going about the y-axis, or pound foot moment going about the y-axis, and then our last step is to apply our reaction forces. So we have a cable that goes from point B to point C. So we'll have it will go along the direction of point B to point C, and then we would have a bearing at A. So since A has a single, is the only bearing, so only one bearing. All right, it will be able to apply a couple moments. All right, now since this bearing, or this pin, sorry, it's a pin, not a bearing, but since there's the pin at point A, the axis the pin goes along is along the y-axis. So it would allow rotation along the y-axis, but it would not allow rotation about the x-axis or the z-axis. So because of that, what we will say for the pin is the pin will prevent translation along the x-axis. So we'll say it can have a moment about the x-axis. It would prevent rotation about the z-axis. So I'll write the moment about the z-axis at A. It will also create a couple moment. Will also apply a couple moment reaction, and then it would also include reaction forces in each of these directions. Sorry, getting the labels wrong here. It should be, these should be the correct labels. All right. All right. And then the last one here is we have a plate that is supported by a journal bearing at a pin or hinge at C, and a roller at B. So if we draw our free body diagram here of this plate, All right, so we first draw the outline shape. The second part is we'll define our axes. All right, and then we will then say apply our external forces. So we only have one. We only have one external force in this case of 400 pounds, which is applied in the middle center of the plate. And then we have our reaction forces. So we have, in this case, we have a journal bearing and the hinge. All right. So since we have a journal bearing and the hinge, we have multiple bearings. So there'll be no bearings or pins. So we'll have no couple moments. All right. So what we're left with is the reaction forces. So this journal bearing is aligned with the y-axis, which means it could rotate about that axis. So, so what it would prevent would be translation. It allows translation along the y-axis. All right, so you can look at the table if you're getting confused about how I'm determining the reactions and how they're directed. But if we look at the table, it would resist motion along the x-axis. So I'll write AX as a reaction force and would prevent translation on the z-axis. So I would say AZ. Right? And then we have a roller at B. So for a roller will always apply a force normal to the point of contact. So I'll say that it would be, you can write that force as NB. And then at C we have a hinge. All right, the hinge axis is along the y-axis, so it would allow rotation along the y-axis, but every other type of direction of rotation would not be allowed, or translation. So what we can do is we should include 3 reaction forces. We should have reaction force along the y direction, a reaction force along the x direction, and a reaction force along the z direction. Okay. All right. So that is your free body diagram for this system, and that should conclude this this lecture, or this video for today's lecture. We'll start off with the next topic, which would be topic number 47.